Okay, we are ready to start chapter 2, and this is going to review some acid-base concepts from AP class. First of all, one type of acid-base theory is the Bronsted-Lowry acids and bases, and that works off the basis where an acid is a proton donor, a base is a proton acceptor. So when I look at this equation, and I look at the resulting products, okay, I see that the HBr has donated a hydrogen somewhere because it's not there on the right-hand side. And let me see if I can remember how to get my pen turned on. So I can just circle some stuff as we're going. Okay, so when I'm looking at HBr, and I look at what the resulting product is over here, I see that it has lost a hydrogen. So a hydrogen is nothing more than a proton. So the HBr is going to be the acid, and since the water now picked up that hydrogen, it accepted the proton, the water is going to act as the base. Another example is looking at ammonia and water, and again I'm going to compare what I have on the left side to what's on the right side. What's the difference? So it looks like the NH3 picked up or accepted a hydrogen or a proton. So in this case, the NH3 is going to be acting as the base, and the water is going to be acting as the acid. So water, if you notice, can act as an acid or a base. And I believe the term for that was amphoteric from last year. Okay, some more Bronsted-Lowry acids and bases. Again, I'm looking at what was there to begin with, what's there at the end. And this is sort of showing this same process, but looking at electrons. And when I'm looking at that resulting product, the Br ion, that's referred to as the conjugate base. Acid and conjugate base. And the base would then have a conjugate acid. Probably remember that from last year, acids and bases. So when I'm looking at every acid-base reaction involving a proton transfer or a hydrogen transfer is going to have an acid and a conjugate base, a base and a conjugate acid. We have to have both of those acid-base pairs. Other acid theory was Lewis acids and bases. Lewis acids and bases thought of acids and bases as electron pairs, accepting or donating. For something to be a Lewis acid, we're looking at electron pair acceptor. So that would mean that there has to be some kind of empty orbital somewhere that could take on a pair of electrons. Whereas the base is an electron pair donor. If I look at Lewis structures, I'm thinking about particles that have all these unshared pairs of electrons around it. So they can have electrons to spare to donate to a bond. Sorry, Kirsten. Having a coughing spell. Okay, so the result of an acid-base reaction is often called an adduct, because quite often we're going to see these two things coming together and making a whole new compound. Almost looks like a synthesis reaction. So if I look at a hydrogen ion and a water molecule. So what's going to happen here is the Lewis acid on the left-hand side has empty orbitals, because if a hydrogen has a positive charge, all this is a proton, because remember, a hydrogen atom has one proton and one electron. And if this has a positive charge, that means that it has lost that, and so all it is a proton. So it's got an empty orbital. It's got an empty orbital because hydrogen can hold 2 electrons. So what's going to happen is the water, which is electron rich because it has these 2 unshared pairs, we're going to see water donate a hydrogen or a pair of electrons to the hydrogen. And when this does this, it forms another covalent bond because you're sharing a pair of electrons. And we've got the hydronium ion. Question? Okay. All right. Maybe now a little more complicated. So when you think about Lewis acids, they don't have to worry with donating a proton, but they can, as long as they accept and share an electron pair. Okay. So this previous reaction could have actually been classified as either one. Bronsted-Lowry, donating and accepting a proton, okay, accepting a pair of electrons, donating a pair of electrons. So this reaction could actually have been classified as both. Now, when I look at this reaction, where our Lewis acid in this case is going to be the BF3, because boron, we see, only has 6 electrons involved in this bond, and it can hold 8. So it has some place here that it could do something with 2 electrons. Now, so it's electron deficient to satisfy its octet. But when I look at this molecule, this one's electron rich because of these unshared pairs. So what can happen is these 2 things can bond at that place. So this compound is going to donate electrons to fill this orbital, and I get a new compound. Okay, and what do these represent, Nathan?
The charges.
The formal charges, right? So we've got another formal charge. Or over here, all the formal charges are 0. Now over here, I'm going to have some formal charges now on these central atoms. All right, some other examples of Lewis acids. Iron 3 ion, aluminum chloride, water molecule, or hydronium ion, all are electron deficient. Again, if you drew their structures, you could actually see that. Obviously, this one's electron deficient because of giving away 3 electrons. That's why it has this charge. And when I think about aluminum, if I think about what aluminum's structure looks like if I were drawing a Lewis structure, right? We've got Al, and we've got, I'm not going to draw all of the chlorine unshared pairs, but AlCl3, again, aluminum has only 6 electrons, so it has room for 2 more, satisfy an octet. Okay, so it could, even though this is an ionic compound, it could bond with something else and accept an electron pair there. Lewis bases, looking at things that are electron rich. Okay, notice all of these, they're showing sort of like a Lewis structure, that all of them have unshared electron pairs.